She's calling me. Guess I'll slide away. I've got to feel her touch most every day. She's warm and she's wild, calls me her child. I warm to her touch. She's my mother ocean. How I love.
Before we do anything else, I'd like to introduce Zina Wetzel, and she's going to do a traditional Hawaiian a prayer, a pule, to get us started.
Aloha no Ozina Koinoa Noho Wau Ma Kalaheo. Aloha, my name is Zina Wetzel. I live in Kalaheo, and I wanted to do a pule in remembrance of everyone that perished in the tsunami 3 years ago, in 2011. Aloha kua, aloha na amokua, aloha akua, aloha kapuna, aloha makua, aloha nakeki, aloha lehu, aloha all of our ancestors, our gods, whoever they may be, our parents, our grandparents, our children, and everyone else in the world. We appreciate the life that we have. Thank you for letting us be here and getting us safely to this conference. Please keep everyone safe and give the blessings on all the speakers here on this conference. Please give light and love to all those families that were affected by the tsunami in 2011. Please let them have healing. Please let us unite all of our Pacific peoples, wherever we may be in all these countries that were affected by the tsunami. And please help us all cooperate together. It gave us an opportunity to see how our oceans link us together rather than tear us apart. And it really is an opportunity for our keiki to strive to have a better future for them. So mahalo for everything that we have, and please keep all the families that were affected by that tsunami in our hearts. Amene, amene, amene. We'd also like to do ho'onani, if you give it a chance. If anybody knows how to do ho'onani, you can sing along with us. It goes, ho'onani kamakua mau, ke ki me ka uhane no, ke akua mau ho'o mai ka ipu, ko ke au, ko ke la au. Amen. Mahalo.
The next speaker is Dr. Dulaiova, who's an expert in the background radiation. So this is something she studied before the tsunami event. Afterwards, we'll have Dr. Maximenko, who's an expert in ocean circulation. So without further ado, Dr. Henrietta Dulaiova from UH Manoa.
So if you hit slideshow.
The button's just
Okay, all right. Hello, everyone.
Hi.
Just to give you a little background about me, I have a degree in nuclear engineering and also in chemical oceanography. And for my, I come from the University of Hawaii in Manoa, from the Department of Geology and Geophysics, where even before the Fukushima disaster, I used radioactive isotopes to study Earth processes. Those include surface water, groundwater interaction, currents in the ocean, and similar things. And so because I do have this background working in nuclear engineering and I use radioactive isotopes, it was obvious to me that when the Fukushima disaster happened, that we should follow the fate of it in the Pacific Ocean, specifically how it relates to the environment in Hawaii and the Hawaiian Islands. And so I will give you a couple of details, not necessarily just about tsunami debris, but about the ocean water and also the islands. So there were actually several isotopes released to the environment after the Fukushima disaster, and those that were released in largest activities, and here I would like to say these are activities, not necessarily quantities, so the number of atoms is not the same as how active these things are, just depends on their half-lives, how radioactive they are, so how fast they decay. The isotope that was released in largest quantities was iodine. Fortunately, iodine 131 has only an 8-day half-life, so it went away as quickly as it came. Affecting us, of course. They found it in milk in Hawaii, for example, and in other locations around the globe. But the much larger headache we got from the cesium isotopes that were released, both by the atmospheric explosions, so it went to the atmosphere and then traveled around the globe and got deposited as fallout, and also was released as ocean discharge. And these, there's a reason why exactly these isotopes were released, because of how uranium is being split into two halves in reactors. There was also strontium and other gases that were measured also here in Hawaii. And this was a very severe disaster. As I mentioned already, radioactivity was released both to the atmosphere and to the ocean, and then lots of it, what was released to the atmosphere, actually fell back on the ocean. And here are some estimates, early estimates that were done the first 2 years after the accident on how much radioactivity was released to these different pathways. And as you can tell, we have huge uncertainty on actual sources. And on top of this, we know based on our measurements offshore of Japan and also between Hawaii and Japan in the ocean water that these releases must have continued even after the declared largest discharges to the ocean in April 2011. We believe these discharges went on for many, many months. And compare this to some other sources of cesium to the ocean. To the Pacific Ocean specifically, I would like to point out the largest source, which is unfortunate to compare a nuclear power plant disaster to weapons testing, nuclear weapons testing, but to give you a perspective, during the various tests in the Pacific region on the atolls, as much as 300 petabecquerels of cesium were released. And so back then in the 60s and 70s, this is how our oceans looked. So these are cesium concentrations that go up to 50. The red regions would be 50 becquerels. These are units of radioactivity. So how many disintegrations per second there is in a volume of water. And you see that these concentrations, the activities then decreased as we went on to the 70s and 80s because we stopped the atmospheric weapons tests. And unfortunately for Central Pacific, we haven't had any measurements of cesium in the ocean water since the 80s, so not even after Chernobyl. So it was time that we actually looked into it. And here's one of a composite image that contains our measurements and some others of my colleagues that shows cesium-137 activities measured in the surface of the Pacific Ocean in April and May 2011. And why I emphasize only April and May, because these are the activities that were due to the atmospheric fallout. So releases from into the atmosphere and then falling onto the Pacific Ocean. And we see that majority of the circulation took the radiation north of the Hawaiian Islands, and indeed around the Hawaiian Islands we see levels that are just the remnants of the atmospheric weapons tests from the 80s that stopped in the 80s. So pre-Fukushima, cesium-137 levels in the ocean are 1.5 becquerels per meter cube. And so near Japan, we had as high as 200 in some places. Due to then the later oceanic releases, we had thousands of becquerels per meter cube right next to Japan. And despite the fact, let me jump back here, despite the fact that right after, so these measurements around the Hawaiian Islands were done actually on 2 weeks after the disaster, we didn't see any of the signature of the atmospheric fallout. That's just because it got diluted so effectively. But we know that we did have atmospheric fallout on the islands because of the measurements that EPA and DOH does. They have atmospheric monitors that continuously run. So they ran even before Fukushima. So you see right here on the bottom, we have time before Fukushima. So just plotted data from January of 2011, and you see that this period here, right, is magnified. So we see better the days actually that how the radioactivity is distributed within these days, and so we can tell based on, this is called the gross beta, so all the beta emitting radioactive isotopes that are in the atmosphere and captured on the filter, in this case not distinguishing which ones they are, so this was iodine and cesium and tellurium and other isotopes, but definitely we see an increasing signature in the atmosphere on the island starting at about the 19th of March 19th, lasting to later in March. But then, as you can tell, the activities return to their pre-Fukushima levels. And that's because we had no other explosions, fortunately, at Fukushima. So this puzzled us a little bit at how come we didn't really catch anything in the ocean when we did have this fallout. But of course, the explanation is that it got diluted within the ocean. But we are, of course, concerned then what was happening on the islands themselves, on the land. Iodine was found in milks and also in EPA and DOH monitored also precipitation and other environmental parameters. What we did, we went out, collected algae along the shore. We also measured sediments and soils. And neither in algae nor in the sediments we found detectable amounts of any Fukushima-derived radiation. And what's Fukushima-derived for us is the definite giveaway is cesium-134, because that has a 2-year half-life. So we cannot have any remnants of the nuclear weapons tests like we have for cesium-137, which is a 30-year half-life. So what we look for when we say we don't find Fukushima's signature is that we were not finding cesium-134. But to really, so we had these radioactivity existing in the air. We wanted to know how much really of that fell on ground. And so thanks to Carl Berg, who collected mushrooms for us on Kauai and also on Maui, and we did some collections ourselves on Oahu and the Big Island, we turned to mushrooms. Mushrooms are very rich in potassium, and cesium behaves very similarly to potassium. And so mushrooms bioaccumulate cesium in them. And they, of course, they have a lot of cesium-137 because of the nuclear weapons tests from the 80s and 70s that's still around in the soil. But so we did this special scaling in that we could compare how much new cesium-134 these mushrooms had compared to how much of pre-Fukushima cesium they collected from the soils. And so we find that for Kauai, for example, we see a trend in how much rainfall there is and in the area, or how much rain fell in March 2011, the 2 weeks, the last 2 weeks in March. of 2011 and how much cesium-134, new cesium-134 was found in the mushrooms. So we kind of see trends that rainfall does matter. And Kauai, it's a clear trend with only 3 points though. On Oahu, it's a bit more scattered. For the Big Island, interestingly, those are the green triangles. If you look at this trend and now look at this study that was done in the 80s, this was measured cesium-137 in soils and rocks on the Hawaiian Islands in the 80s. So that was after the nuclear weapons test stopped, and actually this was before Chernobyl. We see kind of a similar trend in soils. So definitely we can tell that there is a relationship between how much rainfall there was in March, and why rainfall is important is that it washes out the cesium from the clouds and from the atmosphere that fell on ground. And although I'm not showing for the mushrooms any absolute concentrations, these are just ratios, I must say that all these levels are definitely way below any health concerns. You can eat these mushrooms without a problem. We only use these as tracers to find the signatures and trends. Then actually let's move on to the ocean environment, and this is something that we did in 2011. Nikolai Maximenko put together a model that looked at tsunami debris. And so let me talk about that a little bit. So the debris was washed off with the tsunami on March 11. The nuclear reactor got in trouble the next day, really, when they started heating up. And the atmospheric explosions didn't happen until the 13th, 14th, and 15th of March, by which time the tsunami moved a little bit offshore, and also a lot of the atmospheric fallout actually happened right at the shoreline, but a little bit to the north of the islands because of how the wind was blowing. And then the largest releases to the ocean happened in April, the first week of April, by which time hopefully, we presume most of the debris moved offshore. And as I said, cesium behaves very, very similarly to potassium. They are really soluble elements. So it's like salt, it washes off of things. That's why it doesn't capture as effectively to metal or plastic. It likes to attach to clay materials, for example. And that's why right now sediments offshore of Japan or near shore of Japan, they are highly enriched in cesium because, as I said, it likes to attach to those clays. And that's why we looked at as a first thing here in Hawaii after the accident at ocean sediments and clays. Anyway, so what we found with this modeled plume of tsunami debris, that was actually the one that doesn't get, it's not getting caught by wind. This is the submerged one, so it's not the floating buoys or boats. These are things that are buoyant in the water and underwater, so they are not carried by wind, but they are carried by currents. That actually the cesium-134 levels were higher where this plume existed, and so perhaps there was some connection indeed with where cesium could be found and where tsunami debris was located in the ocean. And so ever since we have been looking for cesium concentrations across the Pacific, not just between Hawaii and Japan, but also on the other side towards the west coast of US to identify what kind of levels of radiation we find and whether that correlates really with the tsunami debris. And as early as 2 weeks after the accident, we started sampling for ocean water. Surface ocean is where we would expect to see the cesium first, especially in those early times. We sampled at several locations. We had a coastal station right off of Waikiki, and also we sampled 100 kilometers north of Oahu is the so-called Station Aloha. This is an offshore station where there is a monthly crew to monitor biological activity and other things by UH, and the University of Hawaii. And so we got samples from there monthly. And so the early year and a half, we really have a monthly resolution sampling of cesium-137. All these samples had cesium-134 at below detection limits, so we did not find any evidence of the Fukushima released cesium-134. And so now we stopped the monthly sampling because it's obvious that it's not necessarily needed, just because the plume has not arrived yet. We already produced a good baseline. We see how variable the levels are. So now we have a good baseline to which we can then compare any new measurements. And so we did one sample on February 1st that plots a little bit above the background. But it has a high uncertainty. So we'll just have to see on the next sample whether this is an increasing trend, whether it really started increasing, or we can call this equal to the mean, which I would at this point, based on the uncertainty of the measurement. And I will get back to this, where you can follow up on these samples. But anyway, so this really tells us that neither the atmospheric release deposition, atmospheric fallout, nor the oceanic releases have reached the ocean environment or made impact on the ocean environment here in Hawaii. And of course, it doesn't mean it's not coming. There are many papers that have been published on how the ocean releases have been dispersed and traveling with currents within the ocean. What we do is really look at our numbers. We have many more what I just showed you. We really covered the whole Pacific, and we compare our measurements with the models. And this is one of the papers that has levels that are close to what we can measure. And this paper right here predicted, has forecast for actually the whole time period, but what we see here is going out to 2021, so 10 years after the accident, by which we can tell that the radiation will be, so cesium-137 will be dispersed all across the North Pacific. But they also predicted that radioactivity would be showing up just about now in Hawaii. And as I said, that there is some question about that. There were some other papers that predicted that radioactivity would be making it here in 2012 or earlier, and so forth. So there are so many variable models, and so it's so we are working on providing numbers so they can be compared to actual measurements. And so that's why we want to continue. We want to see how good of numbers we can produce for modelers to compare and perfect their models. This is another example that I wanted to point out. This was a paper that was published by a Chinese group that actually forecasted or predicted that the radioactive plume will travel really fast, just shoot across the Pacific and hit the west coast of U.S. as early as 4 years or soon after the accident, and also they predicted very high levels of radioactivity. And so in this case, what we do is we really take our measurements that were done at a time when their models show some numbers that we can interpret and compare that to our measurements. And so, for example, this we definitely discarded because they the magnitude of the radioactivity that they predicted and the levels did not match our measurements, and so we definitely don't have to worry about this scenario, I think. But then, what do we worry about? And I thought I'd cheer you up a little bit. I mean, I have good news in the sense that we have not seen the radioactivity yet in Hawaii, although it is coming, but the levels will really be below any levels of health concern. So when should we start getting concerned? So I've been naming the unit becquerel. I've been using that so far, and that really just indicates how radioactive the water is, so how many disintegrations happen in a mass volume of water. But really what we are worried about, what it does to us or fish. And so hence we come into a term called dose. What's the radiation dose we get from eating a fish that has radioactive isotopes in it? we actually get radioactivity from all different sources. Dr. Berg already mentioned there is some natural radiation, and so definitely radon is one of the elements that give us the highest dose in general for average population. That's a radioactive gas. It's a noble gas that comes from rocks that have uranium, and all rocks pretty much have uranium and some thorium in them. And so as those decay to radon, that diffuses into houses. And here in Hawaii, we use good ventilation, so we are not necessarily concerned about, but we still get it in our groundwater that we drink and the air that we breathe. So we get some dose from radon, also just construction material around us. I use for my class that I teach on radioactivity, I use no salt that has potassium-40 in it for students to demonstrate that the radioactivity is all around us, in us. We eat it when we use no salt, which is really potassium chloride when you cannot have high sodium intake. So we get radiation from all these different sources. And of course, medical exams, x-rays, and other procedures that involve radioactivity, radiation, cause doses. And so what happens is that the radiation actually hits the DNA cells, and it has to repair itself. And if it has to repair that too many places, then it's a concern because it might make mistakes. That's how the problems arise, such as cancer and so forth. So again, to put it in perspective, what is the cancer risk from radiation? If you have a population of 10,000 people and every single individual is exposed to 1 rem, rem is the unit of a dose, a radiation dose, over their lifetime, from these 10,000 people, 8,000 will not get cancer, 2,000 will get cancer, but from other causes, not from radioactivity, not the radioactive dose, and about 5 people will get cancer from radioactivity. Now, 1 rem over a lifetime is actually quite low. We are getting more than that from just natural radiation, because the background radiation is about 0.3 rams per year. An X-ray, for reference here, is about 0.01 rem. So definitely already from baseline radiation, we get a dose that can be, that accounts for some of the cancer. And so going back to the ocean, as I said, we have all these other isotopes that are naturally in it. Potassium-40 is the one that has the highest activity in the ocean. It has 10,000 units. On this graph, what we see is the scale is logarithmic, therefore you have to multiply by 10 to get to the next level. So potassium-40 is 10,000 becquerels per meter cube. There's also a lot of uranium dissolved in the ocean, 2,000 becquerels. Cesium-137 pre-Fukushima, as I said, was 1.5, and the predicted levels that will reach us, the Hawaiian Islands, if the models are right, and actually it might be lower based on our measurements, would be about 10 becquerels per meter cube. So I just wanted to show you this, that although we can measure it, it doesn't mean it's necessarily adding all that much into the dose we are already getting from the ocean. And of course, no one drinks or eats the ocean. But we still get a dose by eating the fish that's in the ocean. There was this paper in 2012 that was published by Ken Bissler, my colleague from the Woods Oceanographic Institution. They compiled all the data on fish that was monitored up to then on the Japanese coast. Fukushima Prefecture, of course, had the fish that had highest count rate of cesium-137. The dashed line in each figure indicates the limit that the Japanese government decided that they should use as what fish is safe to eat and what is not. So anything that's below 100 becquerels per kilogram of fish would be safe to eat, not give too high of a dose to a person. And so really it's the 3 prefectures, Fukushima and the one north and the one south of it, that really had high cesium levels. You might have heard the news. In 2012, there was a paper that was published on measuring cesium-134, so definitely a Fukushima signature of the coast of California in a bluefin tuna, Pacific bluefin tuna. And Actually, again, the levels in it were really, really low, only a couple of becquerels per kilogram. And although the pre-Fukushima level was lower, so on my figure right here, the blue lines indicate pre-Fukushima levels, and the red lines are post-Fukushima bluefin tuna. And so only the post-Fukushima bluefin tuna had, or the bluefin tuna caught post-Fukushima in August 2011 had cesium-134 in it, and cesium-137 at a much higher, about 10 times higher level than pre-Fukushima. And the conclusion of their paper was, when they calculated the dose a person would get by eating this fish, is that definitely the cesium levels are below any health concerns. The highest dose a person would get from eating this fish would be the naturally occurring polonium isotopes. So again, even if we start seeing cesium in fish in Hawaii, it doesn't mean we have to stop eating it if we are aware that it naturally would already has some radioactivity in it. So it's all about the dose and how much of it we eat. And I believe that's my last slide. But what I wanted to also show you is among the many websites that we work on, this is one that was set up by Ken Whistler from the Woods Oceanographic Institution. You might have heard of it or saw it on the news. So we are part of that, the University of Hawaii. We are actually processing all the samples that are collected here in Hawaii. And you can go, okay, so the background on this is that all these levels in the ocean are below levels of health concern. So the government is not necessarily willing to invest large money into monitoring it because it's not going to cause harm to people. But we are still interested in, even if it's low levels, how low are they? We have to know that it's really low. So it does make sense to at least have information on that. And so because the government is not paying for it, Ken is crowdsourcing, and he's actually accepting donations to create sites. And so you can go onto this website, look at all the existing data. So I pulled up the one that we just recently did in Kaneohe Bay on Oahu on February 1st. So you can actually go and look at many other sites, the west coast of the US, and also all our previous results across the Pacific. But this will always show you what are the levels that were measured. So if cesium-134 is below detection limit, that means it's probably not, the cesium-137 is not Fukushima derived, but the pre-Fukushima. And I just clicked on year 2011, so we also have some results there, and 2012. So you see some of our results here between Hawaii and Japan. So you can go on this website and look at individual sites and learn about them. I guess I take questions. Yes.
Thank you very much. That was a very excellent presentation. I'm curious about the slide of the model that Rossi published in 2013, predicting April 2014 stuff will start arriving. The data is from just the one pulse of the meltdown, or are they taking into account that there's a lot more stuff pouring in, and the Japanese are slowly but surely admitting that they're even releasing more and more? So I don't see exactly how you can say what you're saying.
Could you repeat the question?
Sure. So the concern is that the Rossi paper only used as a source function. So what was released to the ocean, this event of oceanic releases in April of 2011, when we know that there were more releases happening afterwards. And so my response to that is that for the arrival time, it should not necessarily matter because the releases were afterwards. And also the dose, the amount released, that was the highest, the April one. So what was released after that was already a lower amount. But so we might be seeing a much longer tail than what they predict.
As I understand, even yesterday in Japan Times, there are people protesting in Tokyo, and even the TEPCO workers are protesting because there's a lot of information that wasn't shared. And this has been a real problem.
Yes, that is correct. That the information from TEPCO is not really shared with the public, and I also believe many of it, they don't know that they have leakages.
And then the second question was on the next slide. You said the radiation, you showed different places, and from just various medical treatments you would get more radiation. But living near a power station was way at the bottom, and I find that very hard to believe. That there wouldn't be much dosage from someone living near a power station.
So,
Nuclear power station.
so nuclear power plants have very good shielding materials, so they build huge amounts of concrete around them, and actually it's also going to the basement, so they build a good base and then walls also around it, and they have continuous monitoring of doses at the territory of the power plants, and indeed you find lower doses of radiation in the location of the power plant because you are very well shielded from the bottom, from the rocks also. It's common in many nuclear power plants to have lower radiation.
My father was a plant physiologist in Washington State, and he once received a phone call from Hanford, which is not a nuclear power plant, but they said, what are we going to do about his tumbleweeds? Tumbleweeds have very deep roots, and when they break off and tumble around, they were carrying radioactivity in them and blowing around the state. So there's a lot more to this than just putting up the cement barrier.
Right, so Hanford, it's reprocessing, right? So they opened so it's a completely different thing to having it enclosed in a nuclear power plant where they already get the fuel as sealed. Unless there is an accident, that fuel rod will not necessarily leak out. Once you open it, then it's a whole different story. And yes, indeed, there have been known many leaks from reprocessing plants, yes.
Hi, my name is Doug Nelson. I have a few questions. One was along her lines that plume was based on the tsunami and spreading out. But according to my studies, my research, there's over 400 tons of water a day being poured on 3 nuclear meltdowns, China syndrome, 3 neutron stars that can't be put out by mankind. Only God can put those out if you wanted to go, okay. So they've been dumping that amount. TEPCO says 400 tons a day. Well, that's been going on 3 years. They just admitted this recently. And so I would think that the plume model should include that, and I don't think it's in there. Is that correct?
That one was not included in the Rossi model,
Right.
and I'm pretty sure we will have plenty more models being published. And
It's pretty concerning. You know, mankind does not have the technology to put out this. And nuclear energy is a crime against humanity. What a stupid way to boil water. You know, at any rate, the Chinese have banned Pacific seafood. What's your take on that?
First, I would like to respond that any other fuel sources or power sources have their problems also. It's not necessarily that nuclear power plants are the only evil here. Carbon, CO2 might be just as bad, right, in large quantities. And then about seafood. So it's hard to monitor all the fish that is being exported, and I think what the Japanese are doing now is that they have the fishermen going out of Fukushima and catching fish, and until they have a good enough and long enough time of a low dose or low amounts of radioactivity in that fish, they will not let them continue fishing off Fukushima. So they are definitely trying to keep that in check. Fish caught elsewhere, such as around Hawaii, I don't see a reason, unless it's a migratory fish coming, not living in waters that we know does not have Fukushima-derived radiation. I would not be worried about, for example, that. Definitely, we do not have the best understanding of how fish bioaccumulate cesium, so there is also studies on that, because the water that will have a certain amount of cesium that's not harmful, but the fish live in it, they accumulate it, so they will definitely have a higher level in them. So what's that factor is not that well understood. So yeah, there's a lot to learn still.
Another question, that we have yellowfin here, we don't have bluefin. Has the yellowfin been tested here that you know of?
I know yellowfin of one study that was in connection with the Pacific bluefin tuna testing that they did in California. They did the yellowfin tuna testing as a control, since those don't migrate from Japan, and they did not find any Fukushima-derived cesium-134 in them.
What's your standard nuclear energy?
I think that's getting perhaps beyond
Okay.
I think you're over your question limit.
Thank you very much.
And besides, I should say, we're not here to talk politics. Personally, Dr. Berg invited these people because they're experts in their field on their subject matter. So our personal opinions on nuclear radiation are kind of irrelevant, I think, at this point. Okay, thank you.
Yes.
So you've been monitoring, or your group has been monitoring cesium. I was just wondering, a typical Geiger counter like this here, what is it measuring? Is it measuring a certain isotope or like whatever, can you explain that? Because I've always wondered just what a Geiger counter is measuring.
Right, so there are 3 modes of decay, alpha, beta, and gamma. And alpha are very highly charged particles. They have 2+ charge, so they cannot travel easily through even air. They are stuck within the air, and a Geiger counter is not set up necessarily to measure those. You need special chambers to really measure alpha, and purified samples, because it wouldn't even travel outside necessarily of your sample. So Geiger counters can definitely measure very sensitively gamma and beta.
So is it kind of, but they can't like isolate any certain.
And they are not isotope specific,
Yeah.
but they are specific in that you can tell that it's beta, not alpha. And the gamma is just an associating decay after the alpha or beta.
Yeah, so it could be kind of this natural background.
Exactly, yes.
Natural
Yes.
source.
Yes.
The radiation, or it could be, so you can't tell that from a Geiger.
No. And so we don't use Geiger counters, we use a gamma spectrometer that's based on a high purity germanium detector, which has a very good capability of telling us what kind of energy it captured, what kind of gamma energy, and that gamma energy is very specific to each isotope. And so that's the one we use. We actually have to analyze 100 or more liters of seawater to really see the levels, the 1.5 becquerels. So what we do is we take the 100 liters of water. We have this method that we developed. It's a sorbent, a filter cartridge, through which we pass the water, and the cartridge captures all the cesium from the water, which is then this small volume that we can put on the germanium detector, and that's how we measure the water.
So you mentioned, I think the website was radioactiveoceans.org.
Correct.
And do they monitor other types of isotopes too, or is it pretty much the cesium?
No, we only do cesium at this point. Other isotopes of that we're thinking about doing was strontium-90. What's happening in Japan now that lots of the radioactive water, contaminated water leaked into the ground where cesium attracts to clays, it sorbs to clays. And so suddenly, before that, cesium to strontium ratios in the ocean were 40:1. Suddenly that switched around. There is more strontium coming out by groundwater seepage to the ocean than cesium, because the cesium is caught on the clays. But that's, as I said, it's much less than the cesium in the plume that's already traveling in the ocean. Until we see cesium here in Hawaii, we will not start strontium measurements.
When actually you eat fish, like sashimi or something like that, and then you eat, let's say, a pound on Monday, and you eat another pound on Wednesday, does it increase the 134s or 137 cesium as the more fish that you eat in your system, or it doesn't raise your elevation of the body?
Right, so definitely the more of you eat, more of the contaminated fish you would eat, the higher the dose you would get, yes.
So risk factor is what kind of risk factor do they use? More of a thyroid problem or?
For cesium, no. So cesium behaves as potassium, so it stays in your bloodstream and muscle. Right, so different isotopes seek different parts of our body. So iodine, the early releases of iodine were of concern because iodine concentrates in the thyroid, and so they were monitoring that definitely. That's why the sodium iodide tablets that were definitely not recommended to take in Hawaii after the accident, because the iodine concentrations were not that high in the releases, but that's why that is. And then we were of course monitoring for actinides such as plutonium that could escape from a nuclear power plant, because those are bone seekers, so they cause bone cancer more. Yeah.
She's calling me. Guess I'll slide away. I've got to feel her touch most every day. She's warm and she's wild, calls me her child. I warm to her touch. She's my mother ocean. How I love her. Often she rages. It's anticipated.